So these graphs here are called reaction profiles. And essentially you can imagine that it's time on the x-axis. It's not really. What's happened to my pen? Reaction profile. You can imagine it's time along the x-axis, and then along the y-axis is the amount of energy that's inside the chemicals. So on the left, just before the hump, if we zoom in on one of these graphs, so this part of this, well, it should be a flat line. These are the reactants, the energy of that are inside the reactants, and this part of the graph is the energy that's inside the products. So then, as it goes up, we've given the reactants a lot of energy, and then they're going to react. So this part of the graph here is when they're reacting, and then it drops back down into the products. So if we have a look at this line here, then that line there from that bit all the way up to the top, we can call that. Let me just give it an arrow to the side as well. We can call that the energy given to the reactant. So the energy given to these in order to make it react. Now that energy is called the activation energy. So I'm just going to write a comment here, which you can click on. So this is the energy given to the reactants to make them react. This is called the activation energy. Now, next on this diagram, once it's got to that point where it can react, it then releases a certain amount of energy. So this amount of energy here, this is just called the energy released. And that's because when you make the products, then they so let's think about it as we had. Let's imagine that we had three. What's the best way to demonstrate this with a diagram? So if we imagine we had this sort of chemical, so we had this molecule, and then we had a separate molecule over here, which we're going to call orange. We're going to make it orange, and just shrink that down. So this is what is there after the react at the beginning, right? So that's, whatever it might be. Let's say it could be some metal reacting with, I don't know, like iron reacting with magnesium oxide. Well, magnesium reacting with iron oxide, for example. Now, what happens after that is, they all separate. So when you've given them activation energy, they're all separate. Okay. Next, once they make the products, maybe they're going to make in some other form. Maybe they're going to all join together. Who knows? I don't know. But they're going to make these bonds. Now that releases energy. Okay. So we're going to write a comment here that says making bonds releases energy. Okay, so it always drops down after the hump because it's making those bonds, and it always goes up originally because it needs to break the bonds in the first place, and that takes energy. Now because we can see here, and so let's just have a look at this one on the right. Again, I had to give it some energy to get the reaction started. So that bit there would be the activation energy. And then it releases that energy and to make the products. But the difference is between the first and the second one. The first one, the amount I've put in is more than the amount I'm getting out. So overall, I'm losing energy. Whereas on the right, the amount I'm putting just a little bit in, but I'm getting a lot more out. So I'm going to get more. So afterwards, the energy that's given out is going to be more than what I put in. So overall, this is going to take energy in. This is going to give energy out. So this one is endothermic, and this one is exothermic. So let me just write that down. So this is endothermic. So that's endothermic because overall there is energy. The energy that I'm putting in is more than the energy that I'm getting out. And so it would actually, in the way you'd experience that is it would actually feel cold because it would be taking energy from around, and so that it would be cooling down. And this is exothermic because it's releasing more energy than you're giving it.